Hi, my name is Jackson Rankin, um, and I'm a physics student, and I have decided to try and learn a language called R. And R is um, a language for computers, and it's mostly used for data science and stuff like that. So what I've decided to do is, and being a physics student, I deal a lot with uh, data and data interpretation. And so I mostly have used Python for that, but I've also heard that R is pretty powerful. So what I've done is I wanted to do something on theme for my major. And so what I've done is I downloaded something called a Hipparcos catalog, and it's a catalog of about 118,000 stars, and it gives us a bunch of information. So I decided that I wanted to make an interactive sort of three-dimensional plot. Um, like if you go to www.desmos.com slash calculator. Um, that gives you like a 2D, or you can also go to there's a 3D plot for Desmos. Essentially wanted to do that, but it'll plot stars instead of functions. Um, so anyway, here is my code. Um, and this is here's my main, and essentially we use it'll spit out a hipparcos.html, and if you open that up to um, um, if we just open that up using I'm using Firefox here, but you can use whatever you would like. um, you can see that there is a galactic plane here. There is sort of a sort of general area, general plane where the stars orbit. Um, and we also see that there's a bunch of stars right around here, which is this area is called the galactic bulge, which is just an area of stars, near the center of our galaxy, where, if we just look at our galaxy, there's the galactic bulge. So we actually see this in um, more galaxies than our own. Um, let's see, I think the Sombrero Galaxy has a good view of, yeah, right here. So this is taken by Hubble. We can see that this has there's a galactic bulge right around here. All this stuff is called the galactic halo, um, which is just a bunch of stars. But, we have our plane, our bulge, and our halo. Um, and we can see, that we have a plane right here. We have a bulge and somewhat of a halo, actually. Um, so that's my first sort of project. My next one is I wanted to sort of normalize this data so that it's the exact same distance away. So every star is the exact same distance away from the center, from the origin, and which is this part right here. So I made a new file, except this time I made just one um, um, I made the distances from the center exactly the same, and I plotted them, and this is what I got. And if you notice closely, you can see that there's a region of higher density of stars, um, and that's again our galactic plane. Um, if you go out someplace dark and you see, oh, that's the Milky Way ahead of above us. That's that sort of region of stars where it's more dense. Um, so you can see that there is just one band right here where there are more stars than the other two relatively empty parts. And my last one was I wanted to make an HR diagram, which again, using information I got from the .csv file, one of them was spectral type. O, B, A, F, G, K, M all describe essentially the characteristics of the star and most notably color. Um, and so you can see that O type stars are bluer, and then, A stars are, pretty much white, and then G stars are here. This is actually misleading G stars are pretty white, actually. Our star is a G star. It just looks yellow to us because the blue light is sort of scattered in our atmosphere. And so not as much blue light is reaching our eyes. So it looks yellow to us because it's not as blue as it is because of our atmosphere. Um, so our star is a G2, which falls right around here on this spectral line. Sorry, on this HR diagram. So what I wanted to do is essentially make an HR diagram. So if you go back to our code, you can see I made a Hipparcos HR to HTML. Um, and this is my code. I find, I color them and I do linear interpolation to find, the specific color of each type. And then I make a plot. And so that plot is if I host a live server right here. And as you can see, it looks very much like our HR diagram here. The only difference is that this uses absolute magnitude, which is our um, um, it's essentially comparing each star with each other as if it were the same distance away. So on Earth, we can see, oh, that star is about that bright. But this assumes absolute magnitude that assumes that every star is the exact same distance away. So for example, like our star on the absolute magnitude scale is like a 4.58. But on the apparent magnitude scale, as it appears from Earth, it's like a negative 26. It's mid 20s. It's something absolutely crazy like that. Um, so um, if you um, plotted all of these stars in terms of their color index and their absolute magnitude, you would get a graph that looks like this. And so we notice from spectroscopy that all of these stars right here sort of burn helium, and all of these stars right here burn hydrogen. And so um, using this data, we can assume that if we find a star that is, let's say it's an M-type star, and oh, it's -3 times its apparent magnitude is like -3, we can say that oh, it's probably burning helium, and we can use spectroscopy to confirm that. But it's a very useful graph um, for characterizing those stars. If you go back to the Hertzsprung-Russell diagram, you can see that there are 1A and 1B. Then there are type 2 stars, type 3 giants, type 4 subgiants, type 5 main sequence. Main sequence are those hydrogen burning stars, helium burning stars. All of these here are all helium burning. And then we have white dwarfs, which are um, um, dead stars. They're lumps of carbon that are just sort of cooling off in the emptiness of space. And so that was my project. Anyway, thank you very much.